So finally, we are ready to start testing our research questions statistically. While it took us a while to get here, our earlier steps should never be avoided. That is, no matter how sophisticated you may become as a quantitative researcher, you will always need to examine your codebook, manage your data, and examine descriptive statistics for the variables of interest. In my description of hypothesis testing, where we looked at the association between depression and smoking, we were working with a categorical explanatory variable, the presence or absence of depression, and a quantitative response variable, the number of cigarettes smoked per month. When you are testing hypotheses with a categorical explanatory variable and a quantitative response variable, the tool that you should use is analysis of variance, sometimes called ANOVA. Now that you understand in what kind of situations ANOVA is used, we're ready to learn how it works, or more specifically, what the idea is behind comparing means. The test that you will be learning is called the ANOVA F-test. So let's use another categorical to quantitative research question. Is academic frustration related to major? In this example, a college dean believes that students with different majors may experience different levels of academic frustration. Random samples of size 35 of business, English, mathematics, and psychology majors are asked to rate their level of academic frustration on a scale of 1 lowest to 20 highest. This figure highlights that we will be examining the relationship between major, our explanatory X variable, and frustration level, our response variable, or Y, to compare the mean of frustration levels among the 4 majors defined by X. The null hypothesis claims that there is no relationship between my explanatory and response variable X and Y. Since the relationship is examined by comparing the means of Y in the populations defined by the values of X, no relationship would mean that all of the means are equal. Therefore, the null hypothesis of the F-test is population mean 1 equals population mean 2 equals population mean 3 equals population mean 4. Here we have just one alternative hypothesis, which claims that there is a relationship between X and Y. In terms of the means, it simply says the opposite, that not all of the means are equal, and we simply write H subscript A, not all of the population means are equal. Note that there are many ways for the population means not to be equal. We'll talk about that later. For now, let's think about how we would go about testing whether the population means are equal. We could calculate the mean frustration level for each major and see how far apart these sample means are, or in other words, measure the variation between the sample means. If we find that the 4 sample means are not all close together, we'll say that we have evidence against the null hypothesis. And otherwise, if they are close together, we'll say that we do not have evidence against the null hypothesis. This seems quite simple, but is this enough? Let's see. It turns out that the sample mean frustration score of the 35 business majors is 7.3. The sample mean frustration score for the 35 English majors is 11.8. The sample mean frustration score for the 35 math majors is 13.2. The sample mean frustration score for the 35 psychology majors is 14.0. Here are 2 possible scenarios for this example. In both cases, we have side-by-side box plots for 4 groups of frustration levels. A box plot is a convenient way of graphically depicting groups of numerical data, including the smallest observation of the group, the median, and the largest observation. You can see that each scenario has the same variation or differences among their means. Scenario 1 and Scenario 2 both show data for 4 groups with the sample mean 7.3, 11.8, 13.2, and 14.0, indicated with red marks. The important difference between the 2 scenarios is that the first represents data with a large amount of variation within each of the 4 groups. The second represents data with a small amount of variation within each of the 4 groups. Scenario 1, because of the large amount of spread within the groups, shows box plots with plenty of overlap. One could imagine the data arising from 4 random samples taken from 4 populations, all having the same mean of about 11 or 12. The first group of values may have been a bit on the low side, and the other three a bit on the high side, but such differences could conceivably have come about by chance. This would be the case if the null hypothesis, claiming equal population means, were true. Scenario 2, because of the small amount of spread within the groups, shows box plots with very little overlap. It would be very hard to believe that we are sampling from 4 groups that have equal population means. This would be the case if the null hypothesis, claiming equal population means, were false. Thus, in the language of hypothesis tests, we would say that if the data were configured as they are in scenario 1, we would not reject the null hypothesis that population mean frustration levels were equal for the 4 majors. If the data were configured as they are in scenario 2, we would reject the null hypothesis, and we would conclude that mean frustration levels differ depending on major. The question we need to answer with the ANOVA F test is, are the differences among the sample means due to true differences among the population means, or merely due to sampling variability? In order to answer this question using our data, we obviously need to look at the variation among the sample means, but that's not enough. We also need to look at the variation among the sample means relative to the variation within the groups. So F is the variation among sample means divided by the variation within groups. In other words, we need to look at the quantity variation among sample means divided by variation within groups, which measures to what extent the difference among the sampled groups' means dominates over the usual variation within sampled groups, which reflects differences in individuals that are typical in random samples. When the variation within groups is large, like in scenario 1, the differences or variation among the sample means could become negligible, and the data provide very little evidence against the null hypothesis. When the variation within groups is small, like in scenario 2, the variation among the sample means dominates over it, and the data have stronger evidence against the null hypothesis. Looking at the ratio of variations is the idea behind comparing means, thus the name analysis of variance. The results of the analysis of variance testing the relationship between major and frustration score are shown here. The F statistic circled in red is 46.6. Since we know this is the variability among sample means divided by the variability within groups, this large number suggests that the variability among sample means is much greater than that within sample groups. The p-value of the ANOVA F test is the probability of getting an F statistic as large as we got, or even larger, had the null hypothesis been true. That is, had the population means been equal. In other words, it tells us how surprising it is to find data like those observed, assuming that there is no difference among the population means. This p-value is practically 0, telling us that it would be next to impossible to get data like those observed had the mean frustration level of the 4 majors been the same, as the null hypothesis claims. The p-value of 0.0001 suggests that we will incorrectly reject the null hypothesis 1 in 10,000 times, and we will be correct in accepting the alternate hypothesis 9,999 times out of 10,000 times. So we can confidently conclude that the frustration level means of the 4 majors are not all the same, or in other words, there is a significant association between frustration level and major. So we accept the alternate hypothesis and reject the null hypothesis.
Now that you have a good feel for analysis of variance, let's run the statistical test using SPSS. To do this, I'm going to go back to an example that was covered when describing the process of hypothesis testing. Specifically, is major depression associated with smoking quantity among current young adult smokers? Or, in hypothesis testing terms, are the mean number of cigarettes smoked per month equal or not equal to those individuals with and without major depression? My explanatory variable here is categorical with 2 levels. That is, the presence or absence of major depression. My response variable, smoking quantity, is measured by the number of cigarettes smoked per month and ranges from 1 to 2,970. If we would like to run descriptive statistics of these variables, remember that we would go to Analyze, then descriptive statistics. As a categorical variable, depression would be analyzed using frequencies. And as a quantitative variable, the number of cigarettes smoked would be analyzed using descriptives. Now let's conduct an analysis of variance looking at the differences in smoking frequency for those with and those without depression. To do this, we go to Analyze, Compare Means, One-Way ANOVA. Our predictor, or factor variable, is depression. And our response, or dependent variable, is going to be the number of cigarettes smoked. To help read our results, let's also check the Options button and add descriptive statistics to our results. Now click OK. The first half of the results comes from the optional descriptive statistics. You'll see here that it displayed the mean, standard deviation, and frequency of number of cigarettes for each category in major life depression: 0, no depression, and 1, major depression. Here we see just how different they are. People without major depression smoke on average 322 cigarettes per month, with a standard deviation of 303. People with major depression smoke an average of 353 cigarettes per month, with a standard deviation of 337. So, there are differences, but is this difference statistically significant? Here we go to the second half of the results, the ANOVA. The first numbers are the sum of squares, which is a measure of how well the explanatory variable explains the response variable. Second, the degrees of freedom is the number of different values, or levels, of the class variable minus 1. Third, the F statistic measures the ratio of between-group variance to within-group variance. Finally, and most importantly for the purposes of this course, the p-value that corresponds to the F statistic. So here we see that our categorical explanatory variable, major life depression, has 1 degree of freedom, meaning 2 levels. Our calculated F statistic, called F in this output, is 3.26. The significance probability, or the p-value associated with this F statistic, labeled as sig here, is 0.071, just over our 0.05 cut point. Because my p-value is greater than 0.05, I'm going to fail to reject the null hypothesis and say that these means are equal, and that there is no association between the presence or absence of major depression and the number of cigarettes smoked per month among young adult smokers. If I choose to reject the null hypothesis, I would be wrong 7 out of 100 times, and again, by normal scientific standards, this is not adequate certainty to reject the null hypothesis and say that there is an association. Instead, we're going to fail to reject the null hypothesis and say that there is no association. With a significant p-value, I could have said that young adult smokers with major depression smoke significantly more cigarettes per month than young adult smokers without depression. Had the p-value been less than 0.05, I would know that there was a significant association, and to interpret that as a significant association, I would look back at the descriptives table. If the p-value would have been less than 0.05, I can see that individuals with major depression smoke more than individuals who do not. Thus, I now know from my ANOVA results that 322 cigarettes smoked by people without depression per month is not significantly different from the 353 cigarettes smoked per month by individuals with depression. So I've shown in terms of interpreting a significant or non-significant ANOVA, when my categorical explanatory variable has 2 levels, as it did with depression. For this interpretation, all I need to know is the p-value and the means for each of the 2 groups. But what if my categorical explanatory variable has more than 2 groups? In this example, I'm going to examine the association between ethnicity and smoking quantity. My explanatory variable, ethnicity, actually has 5 levels, or groups. 1 is white, 2 is black, 3 is American Indian or Alaskan Native, 4 is Asian, Native Hawaiian, or Pacific Islander, and 5 is Hispanic or Latino. So, by running an analysis of variance, I'm asking whether the number of cigarettes smoked differs for different ethnic groups. Before we run an ANOVA, let's look at the codebook and run descriptive statistics on the race variable to make sure that we don't need to do any data management. Looks good. Now we're ready for an ANOVA. Since I'm only changing the categorical explanatory variable, that is the only part of the ANOVA that we will need to change. This time the F statistic is 18.28 with an associated p-value of less than 0.00. Well, this tells me that I can safely reject the null hypothesis and say that there is a significant association between ethnicity and smoking quantity. At this point, however, all I know is that not all means are equal. I could eyeball each mean in the descriptive statistics table and make a guess as to which pairs are significantly different from one another. I can see, for example, that the ethnic group with the lowest mean number of cigarettes smoked per month is ethnic group 5, Hispanic or Latino, and the group with the highest number of cigarettes smoked per month is ethnic group 1, white. However, because there are multiple levels of my categorical explanatory variable, you know the f-test and the p-value do not provide any significant insight as to why the null hypothesis can be rejected. It does not tell us in what way the different population means are not equal. My ANOVA results could mean, on one hand, that there's only one significant pairwise difference between groups, for example, between white and Hispanic or Latino. Or on the other hand, it could mean that all ethnic groups have significantly different means for smoking quantity, or anything in between. Note that there are many ways for population means to not all be equal. Having each of them not equal to each other is just one of them. Another way could be that only two of the populations are not equal to one another. In this case, where the explanatory variable represents more than two groups, a significant ANOVA does not tell us which groups are different from others. To determine which groups are different from the others, we would need to perform what is called a post hoc test. A post hoc test is generally termed post hoc paired comparisons. These post hoc paired comparisons, meaning after the fact, or after data collection, must be conducted in a particular way in order to prevent excessive type 1 error. Type 1 error, as you'll recall, occurs when you make an incorrect decision about the null hypothesis. Why can't we just perform multiple ANOVAs? That is, why can't we just subset our observations and take two at a time? We could compare white versus black, white versus American Indian, etc. until all paired comparisons have been made. As you know, we accept significance and reject the null hypothesis at a p-value of less than 0.05, a 5% chance that we are wrong and have committed type 1 error. There's actually a 5% chance of making a type 1 error for each analysis of variance that we conduct in this question. Therefore, performing multiple tests means that the overall chance of committing type 1 error would be far greater than 5%. Here is how it works. Using the formula displayed under this table, you can see that while one test has a type 1 error rate of 0.05, by the time that we've conducted 10 tests on this question, our chance of rejecting the known hypothesis when the known hypothesis is true is up to 40%. This increase in type 1 error rate is called the family-wise error rate. Post hoc tests are designed to evaluate the difference between pairs of means while protecting against the inflation of type 1 errors. And there are a lot of post hoc tests to choose from when it comes to analysis of variance. There's the CDAC and the Holm t-test, and Fisher's least significant difference test, Tukey's honestly significant difference test, the Sheffey test, the Newman-Cools test, Dinette's multiple comparison test, the Duncan multiple range test, the Bonferroni procedure, among others. It's enough to make your head swim. While there are certainly differences in how conservative each test is in terms of protecting against type 1 error, in many cases it is far less important which post hoc test you conduct, and far more important that you conduct one. Let's go back to our ANOVA window. One of the optional buttons that you see on the right-hand side is post hoc. When you click the button, you will be prompted with a list of possible post hoc tests to run. For this simple analysis, the specific post hoc test is less important. I'm going to choose the Bonferroni test. You will see that a third table is added to the output. As you can see, we essentially have a table that compares each of the groups in the independent variable against one another. We can see, for example, group 1, white, compared against all other groups, including the significance value. When we look at the differences between group 2 and group 1, that is, black and white, the first number is the mean difference. So this is to say that people who are black smoke on average 116 cigarettes less than group 1, white. Next, we have the standard error, and finally, the adjusted p-value. Here, it is still 0, so we can reject the null hypothesis that there is no difference between black and white smokers. Looking through the other p-values, differences between 1 and 2, 1 and 4, and 1 and 5. Some of the information is repeated below. For example, the differences between 1 and 2 will be negatively reversed for the differences between 2 and 1, but the significance will remain the same. Aside from group 1 comparisons, we do not see any other significant associations. So our significant differences lie between 1 and 2, 1 and 4, and 1 and 5. Looking back into my codebook, I know that this is between black and white, Asian Pacific Islander and white, and Latino and white. No other relationships are significant. This completes the ANOVA analysis and post hoc test. The ANOVA first told me that there is a significant difference somewhere between my ethnic groups in terms of smoking quantity, and the Bonferroni post hoc test showed me exactly where those differences are. So we have really covered a lot. Let me very quickly summarize analysis of variance. First, an analysis of variance is used when we have a categorical explanatory variable and a quantitative response variable. The null hypothesis is that there is no relationship between the explanatory and the response variable. In other words, that all means are equal. The alternate hypothesis is that not all means are equal. The F statistic is calculated by comparing the variation among sample means to the variation within sample means. If the variation among sample means wins out, the p-value is less than or equal to 0.05, and we have a significant finding. This would allow us to reject the null hypothesis and say that the explanatory and response variables are associated. This can be performed in SPSS by going to Analyze, Compare Means, one-way ANOVA. It's also recommended that you add the optional summary statistics. Finally, if your predictor variable has more than 2 groups, you also want to add a post hoc test option. Now you are ready to test a categorical to quantitative relationship. If your own research question does not include these types of variables, you might want to test the procedure with variables from your dataset that do require an ANOVA. For example, you could look at mean age differences according to any categorical variable in NESARC. Or, treating the grade level variable in AdHealth as quantitative, you can look at mean differences, again, by any categorical variable that you choose. For both Gapminder and the Mars Crater data, there are many quantitative variables, so you might choose to categorize one of them for inclusion in an ANOVA. I promise, whatever types of variables you have, you will be able to test the association with the right tool.